It really is one of the biggest things. Okay, so we're going to be graphing rational functions. We're still in our rationals unit. Today we're going to be graphing rational functions, which you end up doing in calculus with limits. The whole first month of next year, you're going to be tested on, can you do this? Here we go. So we know the shift from a parent function looks like this. F of x is equal to 1 over x. Why is that why is that the parent function? Because that's the most basic non-shifted functions, right? All functions have a parent function, and we can take and shift the parent function around. Now, just because I said all functions have a parent function does not mean that all functions are a shift from the parent function. So, if it doesn't have the form 1 over x, if it doesn't have that format, then it's not a shift from the parent function, and we've got to tackle these differently. Remember how we saw functions that were shifted from the parent function and were not in the last unit, okay? All right, so first we're going to deal with this. Now, everybody, I want you to look at the parent function down here, 1 over x. So first of all, I'm going to talk about where asymptotes come from. So asymptotes are values that your function gets really, really close to, but does not usually cross. So I'm going to say that again. Asymptotes are values where your function scoops in and gets really, really close to, doesn't usually cross. There are instances where it crosses it, but it stays really close to the asymptote, and we'll talk about that. So this one has a vertical. Vertical is up and down. Sorry, up and down is our vertical asymptote. This parent function has a vertical asymptote at x equals 0. Now why? Well, because, guys, what value can we not divide by?
0.
0. So x cannot be 0. So that's what creates, look at this asymptote right here. Do you see how x has an asymptote at x equals 0? So our function gets really close to 0, but doesn't cross 0. It never touches 0. Does everybody see why that is? So this blue dotted line isn't actually there. We just draw it in so that we know that that's what our function gets close to. Now our horizontal asymptote is at y equals 0. Now where that comes from is a little bit deeper thinking. So think about this. If I plug in values, I get something out. I get a y value out. If I plug in, I get out. So if I plug in 0, we know we can't. So moving on, if I plug in 1, what do I get out? X, y. If I plug in 1, I get out 1. If I plug in -1, I get out. Now, if I plug in 2, I get a half. If I plug in -2, I get negative a half. Can you think of any value we can plug in and get out a 0? We can't have 0. Do you see how this is never going to be 0? No matter what we plug in, we're never going to get out 0. So that's why we have this asymptote here at y equals 0. Because our function is never going to be able to be 0. So notice it comes down and gets really close to 0 but doesn't cross it. It comes up, gets really close to 0 but doesn't cross it. Any questions on the asymptotes? Now looking at a shifted from the parent function, it'll have this format, which luckily we already know how to shift all functions from the parent function. So if we have a shifted from the parent function, it's going to have this format, a divided by x minus h plus k, where x minus h is your shift left and right, and we go opposite, just like the shifting for all functions works. And then this plus k is added on the outside of our function. That's what shifts our function up and down. And our sign stays the same, just like all other shifts from parent functions. And this a value that's multiplied in front is our stretch or compression, where it's considered a stretch if a is greater than 1, and it's considered a compression if a is less than 1. Now, a lot of people get caught up and say, well, a is not multiplied in front, but think about algebraically what we're looking at, a times 1 over x minus h plus k. If we're looking at this, don't we multiply straight across? That puts a on top over x minus h. So a really is multiplied in front. Now, one last shift, if we have a negative in the front, or multiplied to a, the negative in front, that's its own transformation. It's a reflection over the x-axis. Remember? That reflection over the x-axis. So if I was to look back at this, and instead of 1 over x, let's say I had negative 1 over x, that would be a reflection over the x-axis. So look what would happen. That would take these values and reflect them down here. So instead of being in quadrant, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4, instead of being in quadrant 1 and 3, if we reflect it over the x, then this will flip up here. And that would put us in quadrant 2 and 4. Does everybody see that? So a reflection over x just puts us in the other quadrant. Any questions on this? So now think about it. If I take and shift this function, I'll literally just be shifting my asymptotes. If I shifted right 2, up 2, then we would have new asymptotes there. All right, now I just want you to see how asymptotes really work. So I want you to go to your calculator, go to y equals. In your calculator, go to y equals, and type in 1 over x. 1 divided by x, everybody. I just want us to explore what an asymptote is really happening here. So we know if you go to, don't hit graph, our graphs go kind of crazy in our calculators if we try to do this by calculator. That's why we do this by hand. But instead, I want you to go to the table of values. So pull those up. You hit second graph. Is everybody at the table of values? Now look at 0. 0 says error, and that's because we know x cannot be 0. That's our vertical asymptote here at x equals 0. Does everybody see? But now let's look as we get larger and larger on x. If we plug in 1, we get out 1. Look, if we plug in 2, we get out 0.5. You're just looking at your calculator. Do you see what I'm saying? If you plug in 3, you get 0.33. Now I want you to continue scrolling for x. So scroll down and look at some large values for x. Scroll down. Do you see how on the right, your y values are just getting smaller and smaller, closer and closer to 0? Cool, that's an asymptote. It's just getting really close to 0. Now go back into your negative directions, -1, -1. Oh, and then we know it's going to come up and go close to this asymptote. And then if you go to -1, -1, -2, -0.5, -3, -0.33, what I want you to do is scroll really far, really large in the negative direction, and notice you're getting closer and closer to 0, but from below. You see how you're getting closer and closer to 0. Scroll up and look. It's getting smaller and smaller. All good? All right. Cool. So now what happens in calculus is they'll say this. So everybody, let's see if you can do some calculus. They'll say, given this function, as x is approaching infinity, where's f of x approaching? As x approaches infinity, where's your function getting really, really close to? 0, isn't it? As x gets larger and larger, aren't we getting closer and closer to 0? X goes to 0. That's called a limit. As x approaches negative infinity, where's your function getting really, really close to? 0, you're right. Now let me change it up here and have something different. You just did some calculus. As x approaches 0 from above, now above coming in hot from above, as x approaches 0 from above, where's your function approaching? Infinity. As x approaches 0 from below, where's your function growing to? Negative infinity. So this is a limit that doesn't exist because as you approach 0 from below and above, it's not approaching the same value. So that would be the limit does not exist. Have you ever seen Mean Girls? You've never seen the movie Mean Girls? She's like sitting there in calculus and daydreaming, and then she goes, the limit does not exist. Well, now you know what a limit is. Something like this. Okay, cool. All right. That was calculus. Okay, let's look at this one with me. Here we go. What's my shift in words? You guys tell me, where are the asymptotes shifted? Right 2? Up 3. Now look at my asymptotes. We know x cannot be 2, correct? Because that would be divided by 0. So look, there's my asymptote at 2. Boom, 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 boom. Now, once again, it's a little bit deeper thinking, but it will never be 3. Why? Because can we ever make this piece become 0? No, like we can't plug anything in on bottom to make the top become 0, right? So we'll never be able to be 0 plus 3, so we're never going to be 3. So then our asymptote is at 3. Now, once again, this is not a reflection over x, so we know it's going to be in quadrant, just like the parent function, 1 and 3. Now look, if I was to plot exact x, y points, once again, we have these x, y points, so over 3 up 4, and then look, over 3 up 4, and then over 4 up 3.5. So do you see, aren't we going to just get closer and closer to 3, everyone? That's how that's going to work. And then it's going to come close to this asymptote, and then look, over 1 up 2, and then over 0 up 2.5. So we're just getting closer and closer to 3, but from a different angle. Does everybody see? And then it will come down by this asymptote. Now let's say I changed this and threw in a negative in front. Then it would just literally go like this and like this. Does everybody see how it's not that hard? Rough sketches is all I'm looking for today. No, I don't want you to be very perfect. So everybody look at this examples. Here we go. Where should my new asymptotes be at? X equals 3 and y equals 5. So look, over 3. There's my blue asymptote. Up 5, there's my asymptote. It wasn't a reflection, so do you see how rough of a sketch I need? I just drew it in. That's how much you need. Okay, so look at this example. In first hour, I just let them try it, but we ran out of time. So would you mind if we just do 1 or 2, then I'll let you go for on your homework. Okay, so just watching. What is the horizontal and vertical asymptote? You say, oh, this is a shift from the parent function, 1 over x. So what's the shift? Right, 4. So there's my asymptote there. And then up 6. So there's my asymptote there. Now you would need to write it out. So think about it. Isn't this my vertical asymptote is at x equals 4, and my horizontal asymptote is at y equals 6. And now let's go ahead and graph it. A rough sketch is good enough. Now you could be very exact if you wanted and plug in some x, y points. So couldn't you plug in 5, see what you get? You see how I get 7? Everybody, you could be exact, but once again, I only want a rough sketch. So you say, there's no reflection over x, so this will be in quadrant 1 and 3. So a rough sketch is good enough. It's going to come up by this asymptote, down by this asymptote. Any questions? Let's do our domain and range. Domain is where's your function growing from left to right? Isn't it going to negative infinity? Negative infinity up to 4. Negative infinity up to 4. Did it ever touch 4? Nope, so not including 4. And then union, didn't it start after that from 4 to infinity for x? Look, 4 to infinity. So then 4 to infinity. I put parentheses because it never touched down at 4. My range is my y values. It's going down from negative infinity up to 6. And then it's starting after that. It jumps over 6 to infinity. Union 6 to infinity. Put your unions in. All good. Okay, let's do one more example, then I'm going to let you go for it on your worksheet. Okay. So everybody describe where my asymptotes are going to be. Left 5, down 6. So we go left 5. So our vertical asymptote would be at x equals negative 5. VA for vertical asymptote. And then down 6. So at negative 6 would be my horizontal. Horizontal asymptote at y equals negative 6. And now we do know that we have a stretch of 8. Our acceleration is getting larger quicker, isn't it? Stretch of 8 and a reflection over the x-axis. I only want a rough sketch. Now, once again, if you wanted to be very, very exact, wouldn't you just plug in negative 6 maybe? On this side of the asymptote, plug it in, calculate it. Couldn't you plug in negative 4 and see where to go? I don't need you to be perfect. I'm looking for a rough sketch. So if it's reflected over the x, instead of being right here, it would be over here next to the asymptotes, wouldn't it? And then normally it's over right here, but now it's reflected over the x. So right here, this reflected over x over here. So it's going to be close to the asymptote. People say, what about the 8? Once again, if you want to be exact, plug in some values and plot the points. It just meant the acceleration got larger quicker. All good. So then domain and range. Domain, negative infinity up to negative 5. Does everybody agree? And then -5 to infinity. Our range would be -infinity up to -6, union -6 to infinity. It means united, both are in the answer. Okay. So I'm going to ask you a question, a calculus question. Let's see. As x is approaching infinity, where's f of x approaching? -6. As x is approaching -infinity, f of x is approaching -6. You're right. As x is approaching -5 from above, our function is approaching -infinity. As x is approaching -5 from below, it's approaching infinity. So does the limit exist at -5? Not approaching the same value, so the limit wouldn't exist right there. You just did calculus. Way to go. Okay, do 13 and 14 on the worksheet and 21 through 22. Guys, you really don't have time to talk. So just do them, and then we're moving on. This is the easy stuff. This is helping you understand where asymptotes come from and what they mean. So everybody, once again, quadrant 1, quadrant 2, quadrant 3, quadrant 4, right? Guys, we should be flying through these. We've got to pick it up or else we're not going to make it through the lesson. Are we almost done with these? You're done. Okay, good. Okay, sweet. So those are easy if it's shifted from the parent function. However, we know not all functions are shifted from the parent function. In fact, it's not a shift from the parent function unless it has the form 1 over x minus h plus k. So if there's multiple x's, it's not a shift from the parent function, and we still have to be able to graph it. Graphing it is a lot more of a process when it's not a shift from the parent function. So that's what we're learning now. Now, we're not going to learn all of it at once because it's too much to remember. It's not hard, it's just a lot to remember. So we're going to learn in sections. Does that make sense, everybody? Do this first, understand this first, and then we'll move on. So everybody, a rational function is a function that you can write in the form of f of x is equal to p of x, some polynomial p of x, divided by some polynomial q of x. Now we know the domain of f of x will be all real numbers except the bottom cannot be equal to 0. So our domain is any number as long as q of x does not equal 0. So any values that make our bottom 0 will be our restriction. So we would say x cannot equal this and this. Does that make sense, everybody? Now, those are what we call discontinuities. So that's all we're focusing on right now is discontinuities. If we have a continuous function or a discontinuous function. So discontinuities, you're taking notes, right? Discontinuities come when the bottom equals 0. Discontinuities happen if where the bottom equals 0. That's the first thing we're going to look at with these type of functions, discontinuities. Now there are functions that are continuous. There is no discontinuity. It never has a gap or a break. That's what makes it continuous. So look at this first example. Y is equal to x squared over x squared plus 1. Right now we're just talking about discontinuities. So everybody look, if I graph this, you see how I never have to pick up my pen. It never has a hole or a break, a gap or a break. It is continuous. Now why is it continuous? I'm about to tell you for your notes. Why is this function considered continuous? There's no discontinuities. That's because the bottom never equals 0. How do I know that for a fact? Let's do some algebra. Let's set the bottom equal to 0. X squared plus 1 equals 0. Solve for x with me. What would I do first? So x squared equals -1. Next step. So x is equal to plus and minus I. Sweet. Now understand, this is the real number line here. So there is no real number that makes the bottom 0. The only way this bottom could be 0 is if we have I or negative I. We're not dealing with imaginary numbers here. So the bottom never equals 0. So there is no discontinuities here. Does everybody understand? We're not getting into, well, how did you graph that right now? We're just talking about discontinuities. Does everybody understand? We'll learn how to graph it later. Okay, look at this one. This one has a discontinuity. We cannot have x equal to what? -2. X cannot be -2. That's a discontinuity. Now there are two types. You should be writing this down. There are two types of discontinuities. There's holes or vertical asymptotes. Now everybody looking at this example, x plus 3 times x plus 2 divided by x plus 2. Do you see how I can now take x plus 2 over x plus 2 and divide it out? That's called removing it. Didn't I just remove it out of the equation? I have a new equation, y is equal to x plus 3. Now remember, we always restrict before we divide out. So we did have a discontinuity at negative 2. Our function cannot equal negative 2. So look, at negative 2, we have a hole. Does everybody see? So a removable discontinuity will create a hole. So now how did I know, okay, it's at negative 2, but how high up or down do I need to go to plot that hole, to plot that point? Well, let's plug in and see what our function is at negative 2. So we would plug it into the new simplified function. So let's plug it in. So we have y is equal to negative 2 plus 3. Isn't that 1? So at negative 2 of 1, we have a hole. Does everybody see? And now I can graph my function. Let's graph it. Now when it's simplified, it was x plus 3. Let's graph that. That's a y-intercept. That's just a line. A y-intercept of 3, a slope of 1, up 1 over 1, down 1 over 1, down 1 over, nope, down 1 over 1, down 1 over 1, down. Does everybody see how this is working? And now we graph it. Why is it discontinuous? Because if I was graphing it, I had a nope. Any questions? Okay, no, good to go. Okay, next thing, looking at this, it has a discontinuity here, just like it did here. The discontinuity here is that x equals 2. Now notice, x minus 2 doesn't divide out with anything on top. That's when we get a vertical asymptote. So I would go over to 2 and I would draw in my vertical asymptote here. So if it didn't divide out, if it didn't remove, it's called a non-removable discontinuity. We can't remove it. That's what creates a vertical asymptote. Questions on that? Holes versus vertical asymptotes. So the discontinuities, so I'm going to summarize that up for you if you need to take a picture of this on the next thing. We just learned the first step of graphing a rational function that is a non-shifted from the parent function rational function. So there are many types. There are continuous and discontinuous functions. First of all, if it's continuous, then the bottom never equals 0. So in our first example, it was a continuous function. We didn't learn how to graph it. Right now we're focusing on discontinuities. The bottom could never equal 0, so it was continuous. And the second one, we had a removable discontinuity at negative 2. What removed it? Well, we removed it by dividing it out. Removable discontinuities are holes at that x value, at that discontinuity value. Then we had non-removable discontinuities when the top did not divide out with the discontinuity on bottom. And that's what created our vertical asymptote. We're going to learn later how to find the horizontal asymptotes and stuff. But we're not there yet. Right now we're just focusing on these 3 things. Are we good? Okay. All right, so let's go through. We're going to focus on understanding that first before I teach you the next piece here. So let's look at number 1. The first step to graphing is determining your discontinuities and if they're asymptotes, a vertical asymptote, or a hole. So let's go through number 1 and see what we're looking at here. So to know, we've got to have this factored out because we don't know what divides out with the top and bottom unless it's factored out, right? That's why we learned that on the first lesson of this unit. So let's factor out the top. What should I pull out? 3x, and then left is x minus 3. On bottom, we'll pull out an x, and left is x minus 1. Is everybody with me? So we have 2 discontinuities here. It's when the bottom equals 0. Discontinuities are when the bottom equals 0. So our discontinuities are at x equals 0 and x equals 1. Now, what type of discontinuities are they? Are they holes, vertical asymptotes, or 2 holes, 2 asymptotes? Let's figure it out. So if it removes, remember, if it removes, it's a hole at that value. Does x divide out with x? Well then, at 0, we have a hole because it removed. So we have a hole at 0, comma something. We know that if we were going to graph this, we'd have to go over 0, but how do we know if we should go up to 3 up to 2, up to 9, down to 7. Does that make sense of what? I don't know where to put the whole cut yet. So now write down your new simplified function, which is 3 times x minus 3 over x minus 1. We want to know what's our function at 0. So plug in 0, everybody. 3 times 0 minus 3 over 0 minus 1. Isn't that negative 9 divided by negative 1? Which is 9. So over 0, up 9 is literally a hole on my graph. Does everybody understand? So we would write, we have a hole at 0, 9. Now, does this x minus 1 remove? Nope. So it's a vertical asymptote at x equals 1. So if we were graphing this, which we're not right now, we're just practicing, I'd go over to 1 and draw that in. We haven't learned how to continue graphing yet, but that's where we're starting out. Questions? Questions? Moving on to the next example then. Look at number 2. First, we're going to factor it. It's done. But on number 2 on your paper, I think it says 3x. Okay, so our discontinuities are at what value? When the bottom equals 0. X equals 0 is my discontinuity. 3 times 0 is 0. That's a problemo, right? Okay, is that a vertical asymptote discontinuity or a whole discontinuity? Well, let's see. Does that remove with anything on top? Can we divide across an addition sign? Nope, so it doesn't remove. So there are no holes because it doesn't divide out. So none, no holes, but there is a vertical asymptote at x equals 0. So if we were going to graph this, we would go to x equals 0 and we would graph our vertical asymptote. We've done our first step. So really we're just learning the first step here. Questions? Okay, let's go to number 3 then. And I'm going to let you do some of those on your own. Let's go to number 3. Find the discontinuities. Are they vertical or asymptotes or holes? To know, we've got to factor this out. So write x minus 4, pull out a what on bottom? Yep, so then left is x minus 4. Now remember, you'll find your discontinuities whenever the bottom equals 0. So where's my discontinuity here? 0, and my discontinuity here? 4. Is this a whole or vertical asymptote? Let's check. Does x divide out with any x's on top? Can we divide across the subtraction sign? Nope. So x equals 0, since it didn't remove or divide out, must be a vertical asymptote. Does everybody understand? And then we have a hole, don't we? Doesn't this x minus 4 and this x minus 4 remove? So we have a hole at x equals 4. 4 comma something. So now write down your new function. This simplified when we removed it to be 1 over 4x. So when we plug in that discontinuity value, 1 over 4x is the simplified function. So now we'll plug in 4 into the simplified function. 1 over 4 times 4 is 1/16. So we go over 4 up 1/16. That's where my hole is going to be. So now if I was going to graph that, we've just been able to do now our first step. We would have a vertical asymptote at x equals 0. We would go over, we have a hole at over 4, up a 16th. We plot that. And then we're going to learn how to continue graphing in a minute. That makes sense? Okay, I'm going to give you a second to do the front page, as many as possible, figuring out your discontinuities, if they're vertical asymptotes or holes. If you learn it in sections, it's not so much to remember. So really grasp it so that when we learn the next step, it's not all blending. So we know that what we've learned so far is that discontinuities come when the bottom equals 0. That gives us holes and vertical asymptotes, right? Second piece to graphing is knowing how to find horizontal and oblique asymptotes. You should be taking notes during this. So horizontal asymptotes will look like this. I like to remember them like the horizon of the sun rises like this. So that helps you remember what horizontal asymptote looks like. And an oblique asymptote will be an asymptote that has a slope, a line with a slanted slope. So it'll have the form y equals mx plus b. This is what an oblique asymptote looks like. We know how to graph lines, so we can draw in oblique asymptotes. Now here are the rules to when you're going to get horizontal asymptotes versus oblique asymptotes. And then I'm going to explain why, because having it make sense is the huge part here. Not memorizing the rule, but understanding it. So right here's the rule. Write it down in case you need to refer back to it. But once again, making sense of the rule is the important part. So, if you have a polynomial a raised to the n power divided by a polynomial a raised to the n power, where m is an exponent and n is an exponent, if m, you should be writing this down and then I'm going to make sense of it, if m is less than n, if the top is smaller than the bottom, then we're going to have a horizontal asymptote at y equals 0. That will always happen. If your top degree is smaller than your bottom degree, you'll have a horizontal asymptote at y equals 0. Write that down, and then I'm going to explain why. So write it down in sections. Just write down this part, and now I'm going to explain why. This is what I didn't understand, and this is what I struggled with in calculus. I remember going over this exact stuff, and I was like, what the heck? So everybody think about it. So if we look at this, horizontal asymptotes are what happen to the far right and the far left, right? As x goes to infinity, where's your function going to grow to? Everybody look, if you have, for example, x plus 3 over x to the 5th plus 2x, our degree on top is smaller than the degree on bottom. Now for fun, grab your calculator and let's type in a large value because we want to know what's happening as we get larger and larger. Let's plug in a really large value, like 100. So type into your calculator. Now I want everyone to listen for a second because this is what's got to make sense to you. If I type in 100 plus 3, is that plus 3 really going to matter that much? 100 versus 103? Not really, right? So really, this doesn't matter that much when it comes to what's happening as x approaches infinity. Is 1,000 and 1,003 any different, really? No. So you get what I'm saying? So just type in, if you want, you could type it in 100 plus 3, but that's unnecessary. You could just type in 100. Divided by, on bottom, we have 100 to the 5th power. Now think about it. 100 to the 5th power is going to be huge. Now something huge plus something small, that something small is not going to make a very big difference when it comes to what's happening. So really, all we have to look at is 100 divided by 100 to the 5th power. 100 divided by 100 to the 5th. What do you get? No, you get e. So 1 e to the negative 8. Doesn't that mean 0.00000008 or 1? Do you see how that's basically 0, everybody? Now, if you plug in a larger number, like 1,000, divided by 1,000 to the 5th, it's going to be even closer to 0. Does everybody understand? So think about it like this. If I take a loaf of bread and divide it by 1,000,000 loaves of bread, what's going to be left over? You divide it up into 1,000,000 pieces. If I say, here's a loaf of bread, and now I'm going to cut it up into 1,000,000 pieces, are you going to get any? I'll give you a piece after I divide it into 1,000,000 pieces. Are you going to get any loaf of bread? No. You're going to basically get 0. Does that make sense, everybody? So something small, dividing that up into many pieces will be basically 0. Does that make sense, everybody? So that's why it's y equals 0. Okay, so I literally don't memorize the rule, I think about it. Then right here, next rule. If your value m is greater than n, so if the degree on top is larger than the degree on bottom, that's when we have an oblique asymptote. That's when we get our slanted asymptote with the slope. It'll have the form y equals mx plus b. So for example, looking at this, x to the 3rd plus 2x divided by x squared plus 4. If we were going to divide this using long division, the first step we would do is divide our leading coefficients. X cubed divided by x squared is x. So do you see how we get something left over? We get x to the 1st. So then let's pretend like we went through and did long division and got x plus 2, for example. Do you see how that would be a slanted line with a slope? Now let's pretend we had a remainder. For example, let's say we divided this and got y is equal to x plus 2 with a remainder of 5. That would be plus 5 over x squared plus 4. Now think about it. We're talking what's happening to the far right and far left of the graph. If I plug in, hold on, that's kind of, you can't see that very good. So we have x squared plus 4. Isn't that how we write the remainder? Now think about it. If I plug in 1,000, 5 divided by 1,000 squared. 5 divided by 1,000 squared, isn't that basically 0? 5 divided up into 1,000 times 1,000 pieces. Basically 0. So that goes to 0. So we would only graph y is equal to x plus 2. The remainder would not have a significant impact on the graph because it basically goes to 0. Does that make sense? Okay, cool. So that's how we would find the oblique asymptote, and then we could literally graph x plus 2 because we know how to graph a line. And then last rule, if m equals n, then we will have a horizontal asymptote, and it will be at the leading coefficients. So look at my example. I'm going to write it bigger. We have 2x squared plus 3 over 4x squared minus x. Now think about it, guys. We could go through the whole long process of dividing this, but doesn't it divide evenly? 2x squared divided by 4x squared. Don't the x squareds divide out? Leaving me with 2/4, which is 1/2. Now, everybody, we know we can't divide across an addition and subtraction sign. I could go through the long process of long division, but then won't I just get a remainder, everybody? Will the remainder be significant? No, so that's why I can just divide out the leading coefficients. Now, think about why that makes sense. If I typed in 100 squared, 2 times 100 squared, divided by 4 times 100 squared, wouldn't your 100 squares cancel out, leaving you with 1/2? So we would have, there's no slope because there's no x. So that's a horizontal asymptote at y equals 1/2. It would just be your leading coefficients that matter. So this really doesn't have a significant impact on your graph. Any questions on that? What? Oh, I see what you're saying. Yes, that's the easiest way to look at it. Yes, we would want our polynomials to be in standard form so we can look and divide them. Look at the leading terms. Yes. Okay, look at number 1. Do we have a horizontal or oblique asymptote? Well, let's look. 3x squared minus 9x divided by x squared minus x. Well, aren't our leading terms the same number? So if we were to divide these, wouldn't it divide out evenly? Now remember, this is not significant. This is not significant as we get really, really large. So wouldn't my horizontal asymptote be at y equals leading coefficient 3, right? X squared divide out evenly. Why is it not oblique? Because there's no x. That's not a slope. Everybody see, not that hard, right? Okay, next one. Let's look at number 2. Do we have a horizontal or oblique asymptote? These divide out. They're the same degree. They divide out. And now, once again, if we were to do this the long way, we could. We'd get a remainder, which is not significant. But they would divide evenly. Wouldn't it be 1/3? So our horizontal asymptote, I'm circling horizontal asymptote, is at y is equal to 1/3. We're doing our coefficients, so that's why it's 1/3. Anyone confused? Now, fun fact for you, really, let's try typing in your calculator 100 plus 4 divided by 3 times 100. You'll get a value that is really, really close to 1/3. The larger you get, the more close you'll get to 1/3. Does that make sense? It really works out that way. Sweet, you guys are doing good. Okay, let's look at number 3. Horizontal or oblique asymptote. Now look, degree on top is smaller than degree on bottom. Now what does that rule say? Horizontal asymptote at y equals 0. Now think about y. We take something small divided by something very large. You're going to divide it up in so many pieces that those pieces are going to basically become 0. Does everybody see? So we would have y equals 0 as our horizontal asymptote. If you don't believe me, plug in 100 and see that you get a decimal so small it's so close to 0. Okay, sweet. Number 4, horizontal or oblique asymptote. If we did divide our leading coefficients here, what would we get? X squared divided by x. X. So that's going to be an oblique asymptote. Now, because we have an oblique asymptote, we do need to go through and actually divide this correctly. Now, remember, we know how to divide polynomials by long division or synthetic division. Degree 1, leading coefficient of 1. So I'm going to use synthetic division. Don't we use 4? Okay, we use the 0, so 4. Put in your coefficients, making sure you're not missing anything. We're not. Add straight down, multiply up, add straight down, multiply up, add straight down. We took degree 2, divided by degree 1. What degree will we have left over? 1. So this is x plus 2, and then plus 13 over x minus 4. So remember, our oblique asymptote, as we get larger and larger, if we plug in 100 here, 13 divided by 100 is basically 0. We don't need to write that for graphing. So our oblique asymptote is y is equal to x plus 2. And now if we were graphing this, we could now just graph that line. All good? Not that hard, just memorizing a lot of stuff and how to do it, right? Okay, let's do one more. Horizontal or oblique asymptote. Let's look at our leading coefficients. X cubed divided by x squared would be x, wouldn't it? So it's going to be another oblique asymptote. But careful, we can't use synthetic division, so let's do long division. So remember, we set up 4x squared minus 12x on the outside of our house. I'm going to go quick. Like I said, you have to remember everything we've learned this year. So inside your house is x cubed minus 5x squared plus 6x. And now we'll do long division. So remember, with long division, you focus on the leading coefficient. So we go off to the side, and we do x cubed divided by 4x squared. What do we get left over? 1 over 4x, right? So 1/4 x. That's what goes on top. And then remember, with long division, we multiply that back down in. So 1/4 x times 4x squared. 1/4 x times 4x squared. Look, a fourth times 4. 1, and then x times x squared. So 1x cubed. All right, moving on. A fourth x times 12x. What's a fourth times 12? Yep, -3, and then x times x, so -3x squared. Now remember, with long division, we want these to cancel out, so we need to change the sign. So we have to change the sign here. We add straight down, -2x squared plus 6x. Why am I going so fast? Because it's long division, and we've already learned it. Now we go off to the side and start over. Leading coefficient divided by leading coefficient. -2x squared divided by 4x squared is, yep, -1/2. So -1/2. Now I could continue onward. It's unnecessary though. That times that is -2x squared. That times that is positive 6x, right? Why is it unnecessary though? Isn't that already in the form mx plus b? So isn't the rest going to be a remainder? So, and there is no remainder, but let's say there was. We don't care about the remainder, so we're done here. So our oblique asymptote, since it has the form mx plus b, we found it. Y equals 1/4 x minus 1/2. Are you guys comfortable? We'll find a couple more of those. Horizontal or oblique? Okay. Find the horizontal and oblique asymptotes, and then we can start graphing. Because now we've learned all the steps to graphing pretty much. So practice horizontal and oblique asymptotes. Putting it on a graph. So here we go, everybody. So we're going to go through, and I'm going to just say graph. Now you literally go in the same steps that you did on the front. The front was setting you up for this is how you graph. So your first step is to find the discontinuities. Now that's when the bottom equals 0. So we're going to find our discontinuities. We know they're either holes or vertical asymptotes. So let's go through and do this first. So my discontinuities are at x equals 5, correct? Is it a hole? No, it doesn't divide out. So there are no holes. Then it must be a vertical asymptote at x equals 5. Everybody with me? So then we go over to 5, and that's what we would do. We would draw in our vertical asymptote. Everybody good? Second step, move on. You would say to yourself, okay, now my second step is to find my oblique. Kind of like squeak there. Oblique. Or I'm not used to talking so much after a long break. Oblique or horizontal asymptote, right? So let's see. 2x divides by x, and doesn't it divide evenly? So we would have a horizontal asymptote at y equals 2. Everybody understand? So that's what you draw next. So we've done our first two steps. Same first two steps whenever you're graphing. Now your third step is I want you to plot some xy points so you know where your graph is going. What's it doing? We know it's going to approach the asymptotes, but where are we looking here? Now there are some important xy points. You're going to want to plot some points on this side of the asymptote and on this side of the asymptote so you know where you're at. So let's plug in over here some important xy points, like for example the x-intercept. These are some points I would always graph. X-intercept and our y-intercept. Isn't an x-intercept when y equals 0? X-intercept is when y equals 0. So let's plug that in. Everybody look at the algebra. 0 is equal to 2x plus 3. You won't be able to use a calculator, by the way, for this on the test. Okay, so solve for x. Wouldn't we multiply both sides by x minus 5? Now think about it. X minus 5 times 0. 0 is equal to 2x plus 3. Does everybody see how no matter what, when finding the x-intercept, if we plug in a 0 for y, we're going to take our denominator, multiply it by 0. So wouldn't be finding the x-intercept just solving the top? Does that make sense, everybody? No matter what, we're always going to multiply that bottom out. So now solve for x. Subtract 3, divide by 2. So wouldn't that be negative 1.5? Subtract 3, divide by 2, everybody. Solving for x up here. Minus 3 divided by 2. So now I know that's a point on my graph. We're going negative 1.5 up 0. Sweet. So now we know we're going to be in this vicinity. And then let's run our y-intercept. Our y-intercept is when x equals 0. Let's do the algebra over here. So that's 2 times 0 plus 3 over 0 minus 5. Won't that be negative 3/5? So we're going over 0, down a little bit. Cool. Now think about it, guys. I could continue to plot xy points. Like let's say I wanted to know what 1 is. I could plug in 1, 2 times 1, plus 3 over 1 minus 5. Do you see how I could continue to plot as many points as I want? However, I know how asymptotes work. So this is coming up. It's coming close to the asymptote. This is coming down and approaching the asymptote, isn't it? Okay, well, we will want to, for sure, plug in at least one x value to the right of the asymptote of the discontinuity. So let's plug in 6. Let's at least plug in 6 for sure. So let's do it. Here we go. 2 times 6 plus 3 over 6 minus 5. 12 plus 3. 15 divided by 1 is, so over 6 up 15. So that's somewhere up here. So don't I know then it must be in this quadrant here. It's not going to cross the asymptotes, right? Everybody good? So it's just plotting x by points. Let's do another one. Here we go. A little bit harder. Here, let's do this one. Write it down once again so you don't get home and you're like, I can't graph. So the first step is to identify your discontinuities. Are they vertical asymptotes or holes? Let's do it. So to know, you've got to have this factored out. So for x divided by, we plot an x. Left is x squared minus 4. Am I done factoring this? Nope, let's continue. So we have for x on top, what do we have on bottom? X times, what is this factor to be? Perfect. Now remember, holes divide out, vertical asymptotes do not. So we have a hole at 0, x equals 0 is a hole, correct? And then we'll come back and find that xy points here. Well, let's just do it while we're here. Our new function is 4 over x minus 2x plus 2. So our hole is at 4 over 0 minus 2, 0 plus 2, which is 4 over negative 2 times 2, which is 4 over negative 4, which is? So our hole is at 0, negative 1. Let's graph that. Over 0, down 1, there's my hole. Now let's graph our vertical asymptotes. There's one at x equals 2 and x equals negative 2. So you would go over to your graph, go to negative 2, you would draw in your asymptote. We would go to 2, draw in our asymptote. Now we're to our second step. Draw in your second Second step is to draw in your oblique or horizontal asymptotes. Okay, let's figure out. Something small divided by something huge is 0. Y equals 0 is my horizontal asymptote. Everybody good? So I would go ahead and go, okay, at y equals 0, I have my horizontal asymptote. Any questions up to there? Now it's just plotting XY points. You're not going to be able to touch your calculator during this portion of the test. So let's think about it, guys. Let's pick some XY points that are going to help us graph this. Now you're going to always want to pick XY points between each discontinuity. On the discontinuities, this, and this. Like these three things. So let's plot a point over here on this side of the discontinuity, maybe -3. So let's plug in -3. Ready, set, go. Now we can plug it in many places. We can plug it in here at 4 over x minus 2, x plus 2, or we can plug it into the original. It doesn't matter. So just plug it in. Go. The quicker you people are, the better. So plug in -3. I'm plotting some points because what if I'm up here or what if I'm down here? We don't know until we plug in some values. So plug in -3, everybody. What do we get out? 4/5. Did we all get that? Yeah. So just go ahead and give me decimals for this, but that's fine. So we're at -3 up a little bit, right? At -3 up a little bit. So don't we know we must be up here? Like this? Coming down next to this asymptote, coming up next to this asymptote. All good? Now we need to plot, this is where people get confused. We need to plot a point between this discontinuity and this discontinuity. So let's go ahead and plot -1. So plug in -1. You can plug it in here or here. Go, go, go. Don't wait for your neighbor to do it. Just give me the decimal. -1 point. -1.3? Cool, so I'm going -1 down 1.3. So now guess what I do know? If this is coming down, then it's starting to come down. It's not gonna randomly go back up. So it's gonna come down close to this asymptote. Everybody good? Now we need to know what's happening between this discontinuity and this discontinuity. So let's plug in 1. Now there's two things that could happen. Let me show you what could happen. If this is coming up, then this means we'd be going up and we would actually cross this asymptote. You can cross horizontal asymptotes. So we might cross this asymptote and come up next to this asymptote. That does happen. It will never cross a vertical asymptote though. Or it could come down. If it's going down, then it could come down and approach this asymptote. So which one does it? Let's plug in 1. We got -1.3. So over 1 down 1.3, so that puts me right there. So it must be coming down next to this asymptote. Now we need to know on this side of the asymptote what we're looking at. So plug in 3, and we get 4/5, I believe. So over 3 up a little bit, so it must be coming down next to that asymptote and next to this asymptote. All good? It wasn't that bad, right? A lot of steps, not that bad. Let's do another one. Here we go. Okay, next one. Let's go over our steps. Everybody stay focused. We want to get through 2 more examples in 10 minutes. First step, plot the discontinuities. They're either vertical asymptotes or holes. See if the top factors, because if it factors, it might divide out with this on bottom and it's a hole. But what multiplies to be 6 and adds up to be -3, nothing. So it looks like the top doesn't factor. If the top doesn't factor, then it won't divide out with anything. So there's no holes. Does everybody agree? Our vertical asymptote is at x equals 2. So we would go over and draw in our vertical asymptote at 2. We've done our first step. Second step, find your oblique or horizontal asymptote. The top divided by the bottom. Does it divide evenly? Yes. Well, no, it doesn't, does it? But it divides out to be 2x, doesn't it? That's going to be an oblique asymptote, so we need to actually do this. I'm going to use synthetic division. 2, -3, 3. Add straight down, multiply up, add straight down, multiply up, add straight down. Degree 2 divided by degree 1 is degree 1. So we have y is equal to 2x plus 1. Isn't that my remainder? My remainder doesn't matter. So now I can literally graph my oblique asymptote. So how do we graph lines? Up 1 is my y-intercept. My slope is 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, down 2 over 1. Okay, so I now have my oblique asymptote. Yes. Well, and you're going to see though it actually doesn't. You're going to see that. Now let's just plot some XY points. Okay, here we go. Plotting XY points. That's our third step. Now I'm going to graph. Are you guys see why I'm picking a point maybe over here on this side of the asymptote? Because maybe it's coming like this, right? Or maybe it's in here, depending. So let's plug in, I don't know, -4, -3, anything over their words. Let's plug in, I don't know, -2. Okay, plug in -2, go. You can plug it in to the original. Everybody do it as quick as possible. What do we get? Don't wait for your neighbor to do it like you are. Okay. Plug in -2 with parentheses. Does anybody shout it out? -4.2. Sweet. So we're at -2 down 1, 2, 3. What? Are you guys good? -3, -4 point something. No, you didn't get that. It's -2. Sorry. -2, -1, 2, 3, 4 and a little bit. So don't we know then that it's next to this asymptote? That's how asymptotes work, right? Now we can plug in as many points as we want. Couldn't we plug in 0? Okay, wouldn't that be -3/2? If I plug in 0, that's -1.5. So over 0 down 1.5, right? So it's coming up, and isn't it going to come? Now you could keep plotting points if you plug in 1, but what's going to happen is it's going to come and follow the asymptote. Does everybody see what I'm saying? Now let's plug in an x value on this side of the asymptote, maybe 3. Let's plug in 3. Go, go. Plug in 3. You can be as exact as you want. You can plot as many points as you want. Does that make sense? So you could have plugged in 1. You could have plugged in 1/2 to be as exact as possible. What'd you plug in? You got 17? What'd you plug in? 3? 12. So over 3, guys, look. Over 3 up 12. Won't that be up here somewhere? So now I know it must be close to these asymptotes. And done. All good? One more. I'm going to put in one more example. It could. It won't though. Depending. But yes. So actually it's not going to cross oblique asymptotes. But so it could have turned out on this one that it went like this. Does that make sense? And it could have went like this. But it didn't. We plotted points. Okay. One more, number 19. Go to your thing. Number 19, we have 5 minutes. Let's see if we can do it. So first step. We need to factor this. Guys, focus. Factor this. So factor the top. X plus 1 and x plus 4. Am I right or am I right? And on bottom, x minus 2, x plus 2. Right? So we would say, do we have holes or vertical asymptotes? Anything divide out. So no holes. Our vertical asymptotes are at x equals 2 and x equals -2. Go, graph it. You guys have your highlighters. Okay, focus. Second step. Oh, this isn't bad. We're almost done already. Don't these divide out perfectly? So so we don't have an oblique, but we do have a horizontal asymptote at y equals 1. Leading coefficients, right? Is everybody with me or is anyone lost? Now all we have to do is plot some x, y points here. Now, with this one, we want to graph a point on this side of the asymptote, of the vertical asymptote. So plug in -3. Somebody on this side of the room, plug in 3. Then maybe we should do our x-intercept and y-intercept. So our x-intercept is when y equals 0. Our x-intercept is when y equals 0. Our y-intercept is when x equals 0. Everybody calculate something. Pick something and go for it. These are the points I'd want to see on the test. Some points similar. You plug in -3, 5.6. Oh, 5.6. Anyone plug in -3? So over 3 at 5.6. When you plug in -3, you got what? Negative what? Did anybody else get similar? Okay, cool. So we go negative. So we go over 3 up 5.6. So don't we know what's up here then? Coming by these asymptotes. We plug in -3. We're at negative something. So that means that this is down here under these under that asymptote and close to this. Everybody seeing? Making sense? And then let's find our x-intercept. Our x-intercept is when y equals 0. So if we set this equal to 0, then our bottoms would be gone because we'd multiply up. So -1 and -4. It's crossing the x-axis at -1 and -4. So I would have drawn that even more exact if I would have waited. Like there. Right? Making sense? Crossed at -4, didn't it? And -1. Now, I'm not sure, though, is this maybe coming up like this? Is it coming down? I do know it's, so let's plot some more points. Do you see how I don't know if it's coming up by this asymptote or coming down or what's going on? So I would plot 0. Oh, we haven't found that yet. That's the problem. -2. So over 0, -2, you said? Sweet. So it must be coming down by this asymptote then. And then is it coming up? Well, it looks like it's going upwards, doesn't it? Not coming back down. If we don't know, couldn't we plug in -1.5? Let's do it, because I'm not sure. Plug in -1.5. You can type it into the original if you'd like. You know that, right? Use parentheses. What do we get? Whoa! I got -1 for the x-intercept, for the y-intercept, when x equals 0. If you plug in 0, guys, when we get -1. Okay, let's fix that. Speak up then. You were right. That's okay though, guys. Did anyone plug in -1.5 for me for x? No one? What'd you get? Yep, 10.5. So we know it's clear up here, you guys. So doesn't that mean it is going to cross and head upward? Do you guys see my point here? You got to use your brains a little bit to know, well, I'm not quite sure where this is going. Perfect timing. That was my last example.